Hello and welcome back again. And this time you can see we have brought to you another very special topic, which is widely popular and widely used in electronic circuit design and electronic system designing. It's for the special purpose of signal processing. And the name of the topic today is Sallen Key filters. So there are two person named as Salen and Key from the MIT Lincoln Laboratory in the United States, who invented and proposed this filter topology, so known as the Salen Key filter topology. So as you can see that before we explain this specific configuration and we investigate how this is connected, how this is created, let us understand what the Salen Key filters are, why they are used, what are their unique advantages, and what their disadvantages are. So before I tell you what Sallen Key filters are, how they work, you must be able to remind our previous models where we had covered the first order and the second order circuits using R and C components and operational amplifier. So if you remember, we have covered R and C filters to create the first order and the second order passive filters. And we have also used the combination of RNC and the operational amplifier to create the second order active filters. So Sallen key filters are also used to create the second order active filters. So we are going to see what is the unique advantage of Sallen key, which we prefer over the op-amp with the RC components used as active filters, as we have seen previously. So the first point that we wish to bring to your attention is the Sallen key filters are derived by the topology of voltage controlled voltage source, is basically VCVS. So as we can recall, the voltage controlled voltage source, as you can see that we kind of you have this kind of equivalent model, and we can see that the output voltage of this voltage source is controlled by some parameter, is proportional to some parameter multiplied by the input voltage. So input voltage is right here. So the VO is dependent on the input voltage Vx, right? That's why we call it as a dependent voltage source. And this is an equivalent model. So the Sallen key filter right over here, this topology, is basically a degenerate form of voltage control voltage source. So we'll see that this filter topology also behaves like a voltage control voltage source. And the advantage of voltage control voltage source is that it has Ri, which is approximately equal to infinity, and it has Ro, which is approximately equal to 0. So input impedance of VCVS is extremely high, output impedance of the VCVS is extremely low, and that's this filter configuration. That's the advantage this filter configuration offers. Okay, now the question is, why Sallen key? So because it can be used to create high order active filters. So as I said before, we can use the op-amp and the RNC components, as we have seen in previous modules, to design those higher order active filters. But why Sallen key? We'll see in a moment the answer. So we can use the Sallen key just like earlier modules. Sallen key filters are also used to create low pass, high pass, and band pass active filters, first order or second order, both. Sallen key filters are easy to implement. And the specific feature that we must note here, the Sallen key filters use the operational amplifier in a non-inverting mode. So we see that here we have used the non-inverting amplifier. This has a gain A, and it has got two input terminals, positive and negative, and we see that this circuit is configured in a non-inverting mode. So because we configured is in a non-inverting mode, we have got the advantage of Ri equal to infinity and Ro equal to 0. So extremely high input impedance and extremely low output impedance. And that also provides the advantage of better stability. The filter is stable over large frequency range of operation. So that's the advantage the Sallen key filters bring to its advantage. Now, we can use the cascading of Sallen Key filters to allow to create even higher order filters. So we can go for third order, we can go for fourth order and nth order, so and so forth. Okay, so that's basic understanding about the Sallen Key filter. So before I take you to the next slide, let me show you how this circuit is configured right over here. So as you can see that this is your configuration, and you have used the difference amplifier with a extremely high open loop gain A, and you configured this block in a buffer stage in a non-inverting mode, used it as a voltage follower. So output voltage is equal to the input voltage VID, right? So we'll see that why we use it as a buffer amplifier, because we have got these two advantages right here. Then we use the Z1, Z2, Z3, and Z4, which are basically an impedances. So here Z is an impedance. Z is an impedance, which is basically you can configure using resistor R, or a capacitor C. So using the specific resistors and the capacitor at specific locations, you can create either low pass, high pass, and band pass active filters. And that's why we see that there is this arrangement. Now, here you see that there is a negative feedback we are using, because output is being fed back to the negative pin of the operation amplifier. At the same time, the output through the resistor or impedance, we would say, is being fed back to the positive pin of the amplifier through this resistor network, impedance network. So there is a positive feedback, there is a negative feedback of this amplifier. Obviously, the negative feedback is there to provide the closed loop gain. In this case, we see the closed loop gain is 1, but we can also use the specific resistor combination right here to provide the gain, and configured is a non-inverting amplifier. Right now, this is a non-inverting buffer, but we can use that. But the positive feedback is used to create the filtering function, and we provide the stability. We have to make sure that the gain of the gain, which is dependent on the values of the impedances, has to be controlled. Otherwise, the circuit may become unstable. Okay, so having said that, let me take you to the next slide right over here. And with that, let me clear all the drawing. So why Sallen Key is so popular? That's the first question that we are getting here. So Sallen Key filter topology is, which is, for example, generic topology as shown in this figure, is popular because of its unique configuration. As I just explained you in a moment, there is a negative feedback, there is a positive feedback, and there are 4 impedances which are configured using either R or C, and R and C both, in fact, and their location determines what kind of filter, whether it is low pass, high pass, and band pass, can be created. So in the Sallen Key, you design a filter, and the filter performance is independent of the op-amp characteristics. In the filter, which is not Sallen Key, which is what we covered in our previous model, that too also used op-amp and the impedances, but not in this specific configuration. In that configuration, you use the op-amp as an integrator. But here in Sallen Key, you use the op-amp as a non-inverting buffer or non-inverting amplifier. So either you can have a gain of 1, or you can set the value of a gain using the combination of the ratio of the resistors, just like a non-inverting amplifier. So because you do this arrangement with the Sallen Key, your filter performance is independent of op-amp, because op-amp is configured as an amplifier, not an integrator. And this reduces the gain bandwidth requirement of op-amp, because you configured it as an amplifier, not an integrator. And with this comes the advantage, you can go for high frequency filter design with Sallen Key topology, because you don't have any gain bandwidth requirement or dependency on the op-amp, and therefore your filter function and performance is independent and is not limited by the op-amp performance. Okay, but there are a few points we need to note. For example, the frequency of operation of this circuit whatever the frequency you design it for. Let's say f equal to 100 kilohertz you design it for, or f equal to, let's say, 1 megahertz, and there'll be a Q factor. So Q factor is the quality factor. So basically, when you design a filter, for example, you design a low pass filter where the transfer function, let's say VO over VN, can be configured like this. So this is the characteristics of a low pass filter. Here is a slope, let's say minus 40 dB per decade, because Sallen Key has a slope of minus 40 dB per decade because there are two poles in the transfer function. Okay, so if here the Q is equal to 1, for example, but if the Q is a little bit high, for example, in the Salen Key topology, so you can have a kind of transfer function graph like this for the Q equal to, let's say, 0.3 or something like that. For even higher Q, your graph may look like this, your graph may look like this, and this is, let's say, the Q equal to 0.7 or something like that. Okay, so the frequency and the Q, here is the resonant frequency, FR, of the filter. So the frequency and Q of the Sallen Key are somewhat independent, but so it means the frequency and Q are independent to each other, but they are very sensitive to the gain parameter. So whatever the gain you set here, either the gain equal to 1 in case of non-inverting buffer, or in case of non-inverting amplifier, let's say you set the gain RF by R1 is equal to 3. So your frequency and Q are a little bit dependent on that. Okay. Now, your Sallen Key topology, is very Q sensitive to element values, especially for high Q section. So whatever the values of the impedances you choose, your Q is sensitive to that. Okay, especially you design a band pass where Q is high, and in that case, there is a parameter variations. But the serious drawback now of this filter is it is not easily tuned. You cannot really tune the frequency. Let's say you design it for a specific frequency and you don't find it easy to vary the frequency and you tune it, because there is an interaction of the component values on F naught and Q. So these component values are sensitive to two values, that is the frequency and the quality factor Q. Okay, so second drawback, only a low maximum Q value attainable. For example, Q equal to 0.5 is the maximum in practical implementation. Okay, so I think we are going forward with a lot of understanding. So let me now clear all the drawing. And here we now understand some analytical expression for this filter right over here. Okay, so what you do here, what you see here, we have got this generic topology, and by the since the amplifier has a very high open loop gain, we see that the two potentials are at equal to two pins, positive and the negative, have equal potential. So potential at the positive pin is V minus, potential at the negative pin is V minus, and the potential at negative pin is also V minus, right? Why? Because the gain is assumed to be extremely high. So these two potentials should be at the same potential, right? And that's what we write here. V plus, that is the voltage at the positive pin, becomes equal to V minus. So here earlier it was V plus, but because of the very high gain, it becomes V minus. And we know that this V minus is connected to the V out. Therefore, we can write this expression. Okay. Since we know that V plus is equal to V minus is equal to V out, we can simply say that this is our equation number 1. Let's say this is equation number 1. Okay. So now we apply, we have this node labeled as Vx. And here we are going to apply the KCL. So there is the current here, there is this current here, and there is this current right over here. There are 3 currents. So the first current is V in minus Vx divided by Z1, which we have written right over here. Let me show you. This is the first term. That current is incoming current to this node, which is equal to the 2 outgoing currents. That is, first, this current is Vx minus V naught divided by Z3. So here we have written plus Vx minus V minus divided by Z2. So here Vx minus V minus divided by Z2. And because of the equation 1, and this is, let's say, this we call it is equation 2. Okay, so by combination of 1 and 2, we plug in the value of equation 1 right over here, because we know that V minus is equal to V out now. So by combining equation 1 and 2, what we get is simply this term is as it is, it's equal to this term is as it is, but Vx minus V minus would be replaced by V out, which is due to this term. And that's why we have got these two, this equation, right? Now we apply the KVL right here in this at this node, which is V minus. So we know that there is this current and then there is this current. So that's why we write Vx minus V out divided by Z2, which is incoming current, is equal to outgoing current, which is V out by Z4. And with this equation, we can simplify to this level, this equation. So Vx from this can be written as Vx is equal to V out in bracket Z2 over Z4 plus 1. Okay. So you have got, let's say, right here you have got this equation number 3. Okay. And you have got equation number 4. Okay. So, no, not this equation number 4. We'll not give it a equation lane. So we know that combine equation 2 and 3. So these two can be combined, and we can see that this is how we will write the final expression. And after rearranging this equation 4, let's call it is equation 4, we finally get the transfer function V out over V in, which is set by merely the impedance Z3, Z4, Z1, Z2, Z3, Z1 plus Z2, Z3. And this is basically a second order linear time invariant system. Okay, so that's how we actually understand it. Okay, so let's move to next slide. Here we understand how we can design the Salen Key filter. Specifically, we will now talk about the design of low pass filter. Okay, right now here low pass filter. So here is the generic topology. So what I need to do, I have to choose the values of Z1, Z2, Z3, and Z4 in such a way that in terms of R and C, so that I will create low pass, high pass, and band pass filters. So right now we are talking about how to make unity gain low pass Sallen Key filter. So here Z1 got replaced with R1. You can see that. Z3 got replaced with C1. Z2 got replaced with R2, and Z4 got replaced with C2. So here is what it is. Z1 equal to R1, Z2 is equal to R2, Z3 impedance is 1 over SC1 in the Laplace domain, Z4 impedance is 1 over SC2 in the Laplace domain. And for a low pass filter, second order low pass filter, the transfer function has a standard form H of S is equal to omega naught square divided by S square plus twice alpha S plus omega naught whole square, where omega naught is undamped natural frequency, which is given by 2 pi F naught, which is equal to 1 over square root of R1, R2, C1, C2. So this is how you can design the filter for a specific frequency. Have a value of R1, R2, C1, C2 to set the frequency of filter. 2 alpha. Alpha is the attenuation factor, which is given equal to 2. Zeta is the damping factor, twice zeta omega naught, which is Q is the quality factor, which is equal to omega naught by Q. After simplifying, you see that you have these, this is the equation 1 over C1 in bracket R1 plus R2 divided by R1 into R2. And the value of Q factor can be calculated once you know the value of frequency of your operation, and once you know the value of attenuation, you can get the value of your filter. And that can be finally set by, if you know the value of R1, R2, C1, C2, you can get the value of filter. So the two things are important. Just choose the values of the components to set the frequency, choose the values of the components to set the Q factor. Okay, so that's it. So we'll take you to the next slide here. So how we do that? General idea is that, let's say I have designed this low pass filter. You see now I have got the values here. I have got the values here. And because I have chosen those values, I have been able to design a low pass filter with a Sallen Key topology, which has a frequency of operation of 15.9 kilohertz and quality factor of 0.5. So how I did that? I said that I have to choose the values of R1, R2 and C1, C2. So usually there are four unknown variables and two parameters are only known. These are my specifications and these are my unknowns. So what I will do that I will choose the ratio of the two resistors and I will choose the ratio of two capacitors. So I will reduce some complexities. Okay, I will just be interested in setting the ratios of the resistors and the capacitors separately rather than choosing their individual values. So here so you see the ratio is 1. The ratio of capacitors is also 1 because they have been chosen to be equal value. So what I did is that I say R1 is equal to some parameter M multiplied by the resistance R. R2 is R divided by M, and here is the multiplication, here is the division. For this capacitor also C1 equal to C multiplied by some factor N, and C2 is C divided by some factor N. So let's say I choose M, let's say, let me write here. Let's say I choose M equal to 1, right here, M equal to 1 and N equal to 2, right here. So it would be like 2, and here it would be like divided by 2, and then Q will be set is equal to 1. All right. So if I say, if I want Q is equal to 0.5, so accordingly choose the value of M1 and M2. Okay. Now, accordingly choose the value of M and N actually. So once you know the value of M and N, plug in that values right here to get the values of R1, R2, C1, and C2. Okay. So because if we do this arrangement, our frequency expression, which is like omega naught, earlier it was like this, R1, R2, C1, C2 in the earlier slide. So that expression gets reduced to only 1 over RC. And the quality factor was also some other expression. We have the earlier expression right here, this one. So this expression will also be reduced to this expression right over here. And based on that, I have designed this. So for these values, for this design consideration, I have got the transfer function of the filter in this form. Hs of s equal to 1 over 1 plus C2 in bracket R2 plus R1s. That's the coefficient of S. This is the coefficient of S square. So you see this value is twice zeta divided by omega naught, which is 1 over omega naught by Q into Q. Here 1 over omega naught square. And then you can also simplify this transfer function to this value. So this is how the design procedure is. Finally, just remember, if you choose this arrangement, the frequency of operation and the quality factor can be set using this, and accordingly you will get these values. Okay. R and C is here. Okay, so you might ask what is R here, what is C here. So R and C is here. You know the value of frequency, let's say 15.9, put in here, then you get the value of R and C. Okay, and then you can get the values of R1, R2, C1, and C2. That's it. Finally, let me tell you examples about how the filters are designed with different topologies. So as you can see that this is a low pass filter. This is a high pass filter. This is with a frequency of 15.9 and Q equal to 0.5. Here high pass filter is designed with a frequency of 72 Hertz and Q is equal to 0.5. Can you see the difference between these two topology? You see, this is a low pass. This is a high pass. What's the difference? I have simply swapped the positions of resistors and capacitors in this configuration. So here R, so here will be C, here C, here will be R, here R, here will be C, here C, here will be R. So just swap their positions to convert from low pass to high pass and vice versa. But for a band pass, you have this specific configuration. You can see now this amplifier is not simply a non-inverting buffer, rather it is a non-inverting amplifier because the gain of this amplifier is set by the means of the resistors RB and RA, and there is a negative feedback here, there is a positive feedback here as well. Now, Same case for the low pass filter right over here. Okay, you see that this circuit and this circuit, what's the difference? Here you have the buffer, but here you have a non-inverting amplifier. So both are Sallen Key low pass filter. So hope you found this video useful. Hope you found this module useful. If you did so, share it with others, and wish you happy learning. Stay tuned for more informative and engaging content like this. And see you again soon with the design of the Salen Key filters using the free spice simulators. We'll also explore some different calculations, different topologies.